data webinar this week. Today is our great pleasure to have Dr. Wang speaking us from University of Southern California. So Dr. Wang started his career in University of Science Technology of China, USTC, and actually he started the journey to the core a long time ago. At the time he was at the USTC, probably a little bit more than 10 years ago. And then he moved to University of California, San Diego at the Scripps Institution of Oceanography. But then he moved to some parts that slightly shallower. And then he, after getting his PhD in 2019, he moved to USC and then dived deep into Earth's core. And that is what he's going to present today. So with that, I will give the rest time to Dr. Wang, and please leave for about 10-15 minutes for discussion. With that, welcome.
Okay, thank you, Johnny, for the invitation. It's my great pleasure to, it's not on with myself. So it's my great pleasure to introduce part of my work during my postdoc here at ZGU. So today's topic is mostly focused on the structure of the inner core. So I will briefly talk about our findings and why we do this study and how we find this specific structure of the inner core. So why we want to study the inner core is because, so we know like our Earth is protected by the geomagnetic field and the from the cosmic and the solar radiation. And the geomagnetic field is generated by the autocore convection. So the original force of the geomagnetic field is from the solidification of from the latent heat and also the light elements from the solidification of the outer core to inform the inner core. So to study the inner core, so we can know how the outer core convex and how the inner core informed. So as a seismologist, the seismic wave is our tool to study the Earth's interior. So as this figure shows, if there is an earthquake happens, we can observe the seismic wave using the seismometers deployed all around the world. So we can see the P wave, S wave, and sometimes the surface wave. Using the information carried by these seismic waves, we know the interior structure of the Earth. So how we can know how can we know the inner core structure? So to use the seismic wave, mostly we will use some seismic core probes. So the first one, we will use something like the transmitted seismic wave, which is called the IKP, which directly goes through the inner core. The second one is we use some of the backscattered energy. So the backscattered energy can be two kinds. The first one is some reflected seismic wave at the inner core boundary, which is the IKP. The second one is some backscattered inner core scatter waves, which is the backscatter energy from the heterogeneity within the inner core. So not at the surface, it's within the inner core. So use this kind of seismic wave, we can study some of the specific structure of the inner core. And then the last stuff is the normal mode. So sometimes I'm not so familiar with normal mode. So normal mode can be also a kind of the tool to study the inner core, like structure, like the velocity and the density. However, the normal mode is not so useful, not so widely used, and especially to study the inner core, we should choose some like inner core sensitive mode. So it's just not my topic, so I'm not so familiar to introduce here. And at the early stage, by using the seismic wave, the seismologists build up the 1D model of the Earth. From the 1D model, we know like the Earth has the crust, the mantle, including the upper mantle and the lower mantle, and separated by the mid transition zone. And we have a liquid outer core, which can be known from the shear wave velocity is 0, and we have the solid inner core, and we can know from the shear wave at the inner core is larger than 0. And I think that within the recent 3 decades, one of the most interesting findings about the inner core is the hemispherical structure. So the hemispherical structure contains 2 parts at the shallow part of the inner core. So the velocity of the eastern hemisphere is faster than the western hemisphere. Second, when we go to the deep part, the anisotropy is quite different. So when we look at this map, so pay attention, the white is not 0, it's like 6, but the red is almost 0, which means at the eastern part, the anisotropy is weaker compared to the western part. And this is all from the body wave study. We used some PKP relatively to transmit it in seismic wave PK capital IKP. And then we can also study the inner core anisotropy hemispherical structure by using the normal mode. If we don't concern about the inner core hemispherical structure, we can only have some the splitting function like this one, which is different from our observation. So only add some hemispherical structure, we can have some similar pattern, which means so from the observation of normal mode, we also require the inner core should have some hemispherical structure. So this is a briefly summary. So this diagram indicates like the hemispherical structure, the east versus to the west. So for the east structure, the velocity should be higher and the attenuation is higher. Also, the shallow part is thicker compared to the west part, but the anisotropy at the deep part of the eastern hemisphere is relatively weaker. So during the recent like 3 to 5 years, I think seismologists realized the inner core should not be like hemispherical structure. There should be some more detailed structure. So I think the first attempt is to try to build up the 2D velocity structure, which is called tomography of the top inner core. So they studied the isotropic velocity of the inner core, which can have the hemispherical structure. But when we look at the some detailed structure, we can find this is not exactly this is not exactly the hemispherical structure. It should be have some higher order structure. So what's next? So beyond the transmitted seismic wave and the normal mode, what we can do. So for here, I will introduce our study because this is not widely used. This is called we use the backscatter energy to study the inner core. So most of the seismic wave, mostly we use is the PK little IKP and the inner core scatter wave. So the PK little IKP is the back reflected seismic wave at the inner core boundary, and the inner core scatter wave is the back scatter energy from the heterogeneity with the inner core. So the first discovery of the inner core scattering is only like 20 years ago. So the first observation is find the LASA array, which deployed this array deployed at the Montana, which is a stable geological setting, and also this is so this network only run during middle 1960s to middle 1970s, which is used for the nuclear test monitoring. So this is a pretty great network. The aperture is pretty large. It's like 2 degree times 2 degree, and each spot is also well designed. Uses a small array with a great geometry. So using this, using the observation from these arrays, the Vadali and the first observed some abnormal energy follow the PK little IKP, which was first identified in the seismogram. To explain this kind of energy, they just put 200 kilometer layer, heterogeneous layer within the inner core, at the top of the inner core, and with the velocity perturbation about 1.2 percentage velocity perturbation, and also the correlation length is about 1.2 kilometer. So they put such a heterogeneous layer at the top of the inner core to describe this kind of the signal. During the following like 10 years, the seismologists try to explore this kind of signal only comes from the inner core. Maybe there are other factors can generate such kind of signal, because we know in the interior of our Earth there are different kind of heterogeneities. Maybe like something like mantle and crust heterogeneities. There are also some topography, especially like the inner core boundary and also the core mantle boundary. So, however, so after the seismologists try a lot of different models and also do a lot of forward simulation, so they can. So the conclusion is only the inner core heterogeneities can generate such kind of signal, which lasts about 10 to 200 seconds. This energy, the energy of this kind of signal is spindle-like. Only the inner core heterogeneities can explain this kind of signal. Look like here. So the black line is the standard mantle model with heterogeneities at the upper mantle, also the lower mantle. But the gray one is the standard model with the inner core heterogeneities. We can find that the difference is only from here. There is some spindle-like energy generated after the PK little IKP arrival time. And in 2008, Peng et al. Revisits the data at LASA. There are 71 earthquakes and 7 nuclear tests recorded at LASA, and they check how many events has the inner core scatter wave and how many events has PK little IKP signals. The conclusion looks like only a small fraction of earthquakes has a PK little IKP signal, about 20. About 14 has the conclusive signal of a PK little IKP, but over half of the events has the signal of inner core scattering. Very recently, Wu and Jessica Ivan, they published a paper to use the US array to search for inner core scattering. And what they find is, of course, there are some observations from the US array, and also they find the inner core scattering observed from the US array compared to the observation from the LASA. The scattering is relatively weak. From this paper, they make a conclusion like the West hemisphere seems to have weaker scattering strengths. So from this paper, we realize the distribution of the inner core scattering may not be uniform through all the Earth, through all the inner core. There could be some maybe 2D variation, maybe 3D variation. This makes us to think about some ways to study the 3D structure or maybe the 2D structure. So this is our topics. We want to build up the 3D scattering strengths of the inner core of the Earth's inner core. So now before we talk about what we do with this study, I think of the tool we use to do this study is the beamforming. So the beamforming is a widely used method for the array to use array to study the Earth. So the general idea of the beamforming is to determine in what direction the energy come into the array. So suppose there is a earthquake far from the array, and when the seismic wave generated from this earthquake come to the array, looks like a plane wave. So we will assert the beamforming is used for determining the incoming angle. So from the geometry of the incoming seismic wave, there are two angles are used to determine the incoming angle. The first is incident angle I, which is the angle from between the vertical direction and the incident seismic wave. The second one is the azimuth. So in seismology, we will transfer these two angles to the snow-list. So the snow-list can be used to represent the incoming angle in seismology. So the beamforming, what we need to do is we need to search this px and the py to make this different seismogram align with each other. Because if only if the seismic wave so coming up vertically, so they arrive simultaneously. So if they have some incident angle, so they will not arrive simultaneously. So there are time shifts. So what we need to do is we need to do a grid search of a px and py and adjust the arrival time. So only at the directions the seismic wave come to the seismic array. So we can have all the seismic record align with each other. When we sum up the energy together, we will get this large phase, and we have the maximum energy of this part of seismic wave. So we can show like this one. So if we align them together, we will have the largest energy, which is red here. So if they are not, so the direction is not correct. So these seismograms are not well aligned with each other. So the peak and the trough we add up together to cancel each other. So the energy in this time window will be very small, nearly to zero compared to here. So this is what beamforming works. And the second one is so if there is an array, especially like LASA, is pretty large. It's 2 degree times 2 degree. So we don't know exactly the topography of the array, and also we don't know exactly the structure just below this array. So we need to correct some effect from this one. So what we do is we can find some antipodal events. The antipodal event is the event which whose epicenter distance is exactly 180 degrees. Theoretically, the seismic wave generated from this earthquake should be vertically arrive this seismic array. However, when we look at the seismograms, they are not well aligned with each other. There are some small time shift. So we will use this small time. So we will store this time shift and align them together, and we will use this small time shift to the seismic wave before the beamforming to make the seismogram well aligned with each other. Why? So when we look at this is the diagram to indicate how this correction works. So this is the LASA. We just use 3 stations. If there is some topography like this one, so if there is some velocity anomaly like this one, so if some energy, so if when we look at the antipodal events, the seismic energy should be just vertically arrive the array. However, consider the topography and also the velocity anomaly. They are not the seismic wave not arrive each station simultaneously. So we'll have a systematically bias. So this is one example to show why we should do the statics. So this is PKIKP beamforming with and without static correction. So with the static correction, so we can find the beamforming energy. The blue dot is the predict incoming angle or the predict snow-list, and the red dot is the beamforming is we do from the seismic we do with the seismic energy. So this is the node correction. We can find there could be some systematically bias. So that's why we do the statics. So from the beamforming here, we always have two dashed circles. So these two dashed circles is pretty useful in this study. So the inner dashed circles, which indicate the slowness, so it indicates the slowness of the seismic wave grazing the inner core. So this the outer dash circles indicates the seismic wave grazing the outer core. So we can know the energy from this from the inner circles are the energy almost from the direction of the inner core. So after we have the static correction and we redo the beamforming for all the events, we call it by LASA. We almost do the same thing following the Peng et al. 2008, but we have the static correction. We have better beamforming. So what we do is a little bit different. First, we need to do the 1D beamforming. And we will check if there is a strong energy burst around the PK little IKP predicted arrival time. So if there is an energy burst, we know, okay, this could be some PK little IKP energy. And then we use a small time window like here to do another 2D beamforming. And we will compare the observed the PK little IKP slowness with the predict PK little IKP slowness, which is one is magenta, the other one is blue. We will have these two slowness, and we will compare them whether they are consistent with each other. The second one, we will use another longer time window. In this study, we use 20 seconds after the predicted PK little IKP arrival time to 100 seconds after the PK little IKP arrival time. First, we will check there are some strong energy like this one, and then we will do a 2D beamforming within this time window and to check whether there are some strong scatter energy, whether there are some strong scatter energy within the direction from the inner core, like this one. So this is the blue dot is the predicted the PK little IKP slowness. So we can find, okay, we have some energy like this one, have some energy from the inner core scattering. Okay, so we will repeatedly do this one for all the events recorded by LASA. And now I will show the first our result. We will compare the PK little IKP and the inner core scattering appearance with the earthquake magnitude and earthquake depth. First, when we compare with the depths, we don't find a direct relation with their appearance with the earthquake depths. However, from here, we find most of our observation, almost all the observations are from the earthquake whose magnitude are larger than 5.5, which make us to it's easy to understand because the earthquake should be large enough to generate strong energy recorded by the seismic array. So from this one, we know next time when we try to study the inner core scatter energy, we should generally choose some large earthquakes. Generally for currently seismic array deployed on the Earth, mostly we use the criteria like magnitude 6. And then we compare our result with the Peng et al. 2008. First, when we compare with the inner core scattering, we find, okay, we just find one event more than the Peng study. However, when we do this study, we find we observe much more PK little IKP arrivals than the Peng study. That's because we do the static correction. We correct the structure below the LASA array, so the PK little IKP arrival could better align compared to Peng study. That's why we have much more observation of PK little IKP. So the next step, we try to find whether there are some spatial relation of the PK little IKP and the inner core scattering observation. First, so this is the map of the earthquakes and also the nuclear test. The blue dots is the nuclear test. Most is from the U.S. and also from the Russia at that time. So because the time is the Cold War, and the most important figure is this one. So these figures compare the observed peak little IQP snow list with the predicted peak little IQP snow list. From this map, we find the observation and the prediction almost consistent with each other, which means the snow list we observed from the peak little IQP arrival, peak little IQP, or the inner core, or the direction from the inner the energy from or the direction of the energy from the inner core are almost accurate. So we can directly use the snow list here. The second one, we just look at all the inner core scattering beamforming, try to see there are some consistent pattern. So, but this is the most amazing part. So when we look at the beamforming of the inner core scattering, we find most of the inner core scattering comes from two directions. One is from the northwest, the other is from the southeast. So when we look at this one, so this is very exciting. So it makes us to think about what kind of 3D distribution of inner core scattering can generate the beamforming, generate the beamforming like this one, or generate the inner core scattering energy like this one. So the straightforward method we think about is just to use the back projection, because the back projection is widely used to do some source kinematic imaging. So this is the first study to use the back projection, study the earthquake kinematic rupture by Miyake Ishii to study the Tohoku earthquake. No, this is not. This is from the Sumatra earthquake. And also the back projection can also be used to study some small scale structure from the core mantle boundary. It has never been used to study about the inner core, and also the methodology should be improved. And now I will just briefly introduce how we improve the back projection compared to previous study. So the back projection here we use is a little bit different from previous one. So assume there is a earthquake in this here, it will generate some downgoing energy. It will arrive some scatter within the inner core. This scatter will generate some scatter energy, arrive the array. And as we know, like the inner core should have a lot of scatterers. So it could be have at the same depths. So if the scatterers at the same depths, so the incoming direction should be different, which means the snow list should be different. And the other case is the scatter can generate the seismic wave almost at the array in the same direction. But this kind of scatter should be at different depths, which means the arrival time is different from between these two scatterers. So from this simple diagram, we know like the snow list azimuth and the arrival time of the seismic of the inner core scatter waves can be transferred to the location of the scatter, like the latitude, longitude, and the depths. So what we do is we just grid the inner core into small grid, and we compute and we assume each grid as scatterers, and we compute the snow list and the arrival time of the seismic wave from these small scatters. And we plot the diagram here. So this is the scatter at different depths, and this is from the inner core boundary. So the 0 point means the inner core boundary point at the inner core boundary. So this is the arrival time from the peak little IKP. So this is from the deep part of the inner core, which means, and also this is all from the coda. There is no 0 time. And now what we need to do is not so hard. So we just grid the inner core. We randomly pick up a scatter, and we know it's 2D snow list. if we know the 2D slowness, we will get the beamformed seismogram, and we will get the beamformed seismogram we plot here, and then we know the lapse time, and we will have the lapse time, and we will use a time for this study. We use a 10-second time window centered at this time, and we get the energy from the envelope here, and we put the energy to these small scatters, and we go through all the scatters, and we put each of the energy on each scatter, and we will do this one for all the events, and then we will have the energy at each of the scatters within the inner core, and we normalize by the heating point, and we will have our final result. This is the normalized scattering energy. From the normalized scattering energy, we know, so this plot is at the center of LASA. So this has the same direction of the beamforming. So from this plot, we may find, okay, most of the strong scattering energy direction is from the northwest and the southeast, which is consistent with our beamforming result. So which indicates the inner core has two strong scattering region. One is almost below Asia. The other one is around the South America. And also when we look at the depths of these two regions is quite different. So the northwest part below Asia is about 300 kilometers. The other part is about 400 kilometers. The depths could be a little bit different. And next, we maybe explore what could be the physical mechanism for these two strong scattering region, or maybe this three distribution of the inner core scattering strengths. We list a different kind of mechanism. First, they could be from the small scale topography. Also, it could be from the partial melt. Also from the compositional variation. So we realize it is hard to use these three factors to describe this large scale distribution. So it's not so easy to directly use these three factors to explain this distribution. However, when we compare the distribution of the inner core strong scatter region with the shear wave velocity at the core mantle boundary or lower mantle, we find so this is a really, really amazing comparison. So we find the strong scattering region are co-located with the high shear wave velocity region at the core mantle boundary, and the weak scattering region is co-located with the low shear wave velocity region. They almost co-located with each other, and the geodynamists can convert the shear wave velocity to the temperature or the heat flux. For here, so the low shear wave velocity can be converted to the high temperature. The high temperature can be the blue region here. The blue region is the heat flux. Because this is the high temperature, we know the temperature almost increase with the depth. So in this area, this is a high temperature, which means the temperature gradient here in this blue region is small, which means the heat flux could be small. And also for the colder region, the colder region, like here below Asia, in this region, the temperature is low, and also the velocity gradient is large, so the heat flux is large. So the geodynamics use this heat flux as a boundary to generate the geodynamo model. And finally, they got an interesting pattern at the core mantle boundary. This this is also, it is not here, this is also heat flux. We know the heat flux and the temperature is different. So the high heat flux means cold region, and the low heat flux region is the high temperature. So we find the cold region at the core mantle boundary are co-located with the strong scatter region. And the warm region at the core mantle boundary are co-located with the weak scattering region. So this makes us to think about the easy physical model. It looks like this one. So the cold region at the core mantle boundary sometimes can generate the downgoing convection. So this downgoing convection flow will arrive at the inner core boundary. This will carry some cold material to generate some cold region around this region and also in this region. And the cold region here will make the inner core grows faster in this area and make the grain size of the inner core smaller in this area. The smaller grain size is easy to generate strong scattering. So they are on the other side. So in the warm region, so the crystallization process is quite slow. It's a slow freezing, and it will, so the grain size will generate larger, and it will generate the weaker scattering. So this is our model. Our model looks like we have two slabs, and we have two plumes, and our inner core scattering could be at a degree 2 structure instead of a degree 1 structure, compared with the velocity attenuation and anisotropy. So this could be a little bit different because we think the scattering is more sensitive to the temperature, which may not be reflected by the other factor of the seismic properties. So this, so when we look at this structure distribution, we realize there's could be problems from the inner core rotation model. So the inner core super rotation is widely accepted. I just called accepted, but it may not be correct. So this is this first discovered from the geodynamo simulation. They find when they try to generate the geomagnetic field, they find the inner core have a super rotate about 1 degree per year. And this behavior first observed from seismologists is by Song and Paul Richard. So when they using the earthquake almost co-located with each other from South Sandwich Island and observed from Alaska seismic network, they find when they align the PKP BC, which only passed the autocall, when they align them together, the PKP AB also pass autocall, can almost align with each other, but the DF has a systematically time variation. To explain this one, they assume the inner core is anisotropy, and also the anisotropy and the axis is different from the Earth rotation axis. So it required the inner core could be super rotate a little bit with 1 degree per year, and also this observation also confirmed by the normal model study. So when they studied the split function from some of the inner core sensitive mode, when they try to check some specific pattern to check whether this pattern move, so they give the inner core move, or they give the inner core some super rotation rate, and to check the split, this specific pattern move, whether they move or not, and to compare the earthquake at different time, and they find the inner core could be super rotate, but at a lower rate, about 0.13 degree per year. Also, from inner core scattering, we can also do same thing. So if the inner core is super rotate, so the inner core scatter, the heterogeneity with the inner core also can move super rotate with the inner core. So the scatter energy could be the seismic. So the inner core scatter wave will also change a little bit. So if if like this case, if the inner core super rotates and also the scatter move a little bit, we can find that sometimes the repass becomes shorter, so the seismic wave arrive earlier, and sometimes it can if the inner core super rotates, the rate path become longer, so the scatter wave will arrive later. So it can also be observed from the inner core scatter waves. So when we have something pattern like this one, it will also help us indicate the inner core is super rotates or not. So based on these assumptions, the Vadali and the they do similar study, and they find the inner core could be super rotate at a relatively lower, also lower rate, 1.15 per year. So this is a conclusion from all the study during these 2 decades. So from the blue dot is the study from the normal mode, the gray dot is from the inner core scatter waves, and the green dot is the seismic body wave or transmitted seismic wave is from the South Sandwich, Alaska. This is the earthquake from South Sandwich and the station at Alaska. All the results can generally merge to the inner core could be super rotate, but at a lower rate, about 0.1 degree per year. So like 10 years ago, there is a study, comprehensive study about the hemispherical structure of the inner core. From this observation at different depths, we find the hemispherical, the boundary of the hemispherical structure is pretty sharp, like here. So we can find this boundary is pretty sharp. However, when we imagine so from the geodynamic or from different kind of modeling, so the inner core growth rate could be 1 millimeter per year. If the inner core is super rotate at a consistent rate, about 0.1 degree per year, so the inner core could rotate 1 cycle at about 4 siren years. So when we look at this figure, for this observation from hemispherical structure, so its persist can go to as low as 100 kilometer. Okay, so which means the inner core could grow about 1 million year. So if inner core rotates 1 circle per the inner core could rotate one cycle every 4 siren years. So this structure could be removed. So we cannot have such a sharp structure. So based on this structure, so if we also assume inner core could be super rotate, the super rotate rate could be very low. It's about 1 degree per million year. So currently the super rotation rate we observe is not consistent with the observation from the structure. Also, from our inner core scattering structure, so these 2 regions can go to as deep as 300 kilometers and 400 kilometers. So also, if the inner core consistent super rotates, this structure could also be snell. So which means the structure, so the observation of the inner core structure is not consistent with the observation with the study from the inner core super rotation. About 2 or 3 years ago, I like this model. This model is the inner core oscillation model. So if the inner core not super rotates, it's just the oscillation. So it's like, because we know the lower mantle has the large low shell wave velocity province. This area, the black area, is a high density region, and because of the gravity, it will pull the inner core in this ellipsoid, and then it's just so if there are some geodynamo, it can generate some the inner core could be oscillate a little bit, but it's like a pendulum, so it's just keep it just oscillation around its equilibrium state, not super rotate. So from this model, we think this could be more easy to accept compared to the super rotation model, but this needs more time to be proved. And we have this is the here. So we find, so we have another paper to claim like there could be some observation from the inner core. It's not exactly super rotate, could be oscillation. but I will not introduce here. But we think that the oscillation could be easily accepted based on, and also to reconcile the model from the inner core structure and the inner core movement. And this is a paper. So this is a newspaper from the Science. It introduced the discovery history of the inner core superrotation study. If you are interested, maybe this could be helpful. And here, I want to say all the models wrong, but some are useful. So, so when you check the development of, when you check the study of the inner core superrotation, we find that more and more models has been proposed, but some of the model can explain some of the data. It's needed more time to make a uniform model to explain all the inner core movements and also the inner core structure. So so thanks for different people like Professor Stoney, Lin Xinwen, John Arnold, Jiao Yuanyao, and Ding Hao, Ben Chao, and Bruce Buffett. And thanks for constructive discussion during the study. And thank you. If you have any questions, please free to ask.
Okay, thank you very much for the talk. Now it's time for questions from participants. So feel free to open your mic and ask a question. And also feel free to post your question in the chat and I could read the question on your behalf. So go ahead. Any questions?
Hi, Wei. Thanks for the talk. It's very, very interesting work. Yeah, as a non-seismologist, I'll ask some pretty dumb questions. But so when you're looking at the scattering of the inner core, I believe you mentioned that you assumed a single scattering model.
Right.
Down to 500 kilometers depth is the lower bound.
Right.
Yeah. So what happens if there's strong scattering below that depth? Does that cause a change in where you would localize the scattering?
Yep.
Yeah.
Very good question. So so this is also a good question. So this is also very so these questions could be answered like this one. So we have a different kind of inner core scattering model currently, a lot of study, different region. And when we compute the the mean free path, which is from the Brownian motion, so which indicates if there are two scattering events happens, there are distance between these two, the distance between these two scattering events. The mean distance is called the framing path. Okay, so the framing path from all the proposed inner core scattering model is over 100. I think, as I remember, it's over 1,500 kilometers. It's much larger than the 5 kilometers, which means it's less likely to happen twice. Which means the multiple scattering is not always happens when the seismic wave propagate in the inner core.
Right.
Yeah.
Okay, that makes sense.
Yeah.
And I guess kind of related to that, I really like that image you showed of basically the pattern, the fingerprints of the inner core scattering in the seismogram has that little bump, that spindle signal. I think that's what you call it.
Yes.
Is it possible for that to be generated by anything else? Let's say you have a hypothesis that there's no inner core scattering. Is there any way that could be affected, let's say, by the higher shear waves in the core mantle boundary or something like that?
Oh yeah, that's good. Also good questions. I think a lot of people have done this study. They try to set up a different here. Sorry, just 1 second. So you mentioned this one.
Yes.
Yes. So I think there are two papers. It's Layton and Cooper. So so what they do is set up a different. So they set up a different kind of model. So they put different heterogeneities at especially like you mentioned, they put some strong heterogeneities at the core mantle boundary. They also put a layer there and try to see whether they have such kind of signal. but the answer is no.
Mm.
So because the most significant thing is here. So this kind of signal can last for almost tenths of seconds. Mostly it's over 100 seconds. And also it's a spindle-like, which means they have a rise time and also decay time. So if we put if we put some heterogeneity at the comment boundary, but we just assume the inner core is homogeneous, we don't have such a kind of signal. This is the only thing we can generate such kind of signal.
All right, yeah, that makes a lot of sense, and I guess that would resolve any kind of ambiguity in your 2-degree model where you have the high shear waves co-located with the intercore scattering.
Yep.
This would basically say that you can resolve those two effects with this data.
Yeah.
So,
yeah.
Yeah, that makes sense.
And also, also another way. So when you look at another thing, just I will add another stuff. So when you look at this one here, so the repass from the earthquakes mostly are far from the strong shear wave anomaly region.
Oh, okay.
At the mantle. So when you look, so we have most of just 1 second. Just 1 second. Here. So most of the earthquakes are in this region, and in this region is far from the Pacific. So it's has less effect from that part region.
Got it. That makes sense. Okay. Thank you.
Thank you. Thank you for asking.
Okay, that's Brian from Zhejiang University. So next question, please.
Hello. Hi, Wei.
Hi.
Nice talk. Thanks. Yeah, I'm just have 2 technical questions. I guess the first one is, since in your paper you use LASA network, right, which is a quite dense seismic network.
Yes.
So I'm just wondering if like other more typical networks, say, US array, China array, and this kind of regular network can also be used to do the back projection.
Sorry, I think the answer is probably no.
Okay.
Let me see. I can show you one result. So this is one result from Jessica Ivan. Okay. So there are 2 reasons. The first one, so the bandpass filter. So the frequency band we try to see the inner core scattering is almost larger than 1 Hertz. It's almost like 1 to 2 Hertz or 1 to 3 Hertz. We used to study the inner core scattering. Okay. So the station distance, the station interval for US array and China array, they always are larger than 10 kilometers, right? So so such a higher frequency seismic wave, it's hard to keep consistent coherence at such a longer distance, right? So that could be a problem.
Yeah, the station distance spacing definitely play a big role. So this actually comes to my second question. So you're basically, this really relies on the coherency in the seismic data, right? The seismic wave.
Yeah.
So I'm wondering if any pre-processing can be done to improve the coherency first, and then apply the back projection.
Good questions. This is what we are doing now. The answer is we are still working on that. So the answer could be not yes, but not no. But we have some achievement, but it's hard to say.
Okay, so it's promising, basically, or it's useful. Put it this way.
Yeah. We have seen something from HiNet.
Okay, so that's from Japan. All right.
Good news is we have seen something from the HiNet, but the problem is the resolution is not as high as the LASA, because the HiNet is just a random distributed, not like a well designed seismic array.
I think wave field regularization and probably some denoising method can help in this regard.
Yes, I read your papers, and also I heard your talk. I listened to your talk at SOSTEC. Okay. So that's promising, I think.
Okay, thanks. Yeah, we can discuss later maybe.
Yeah, we can discuss later.
I'm quite interested in this.
Yeah,
right.
Of course.
Right. Yeah, thank you. Sorry, my internet connection is poor. I'm in the hotel room. So
okay, thank you for asking.
Talk to you later. Yeah. Thanks.
Okay. Next question, please. Deng Jie, please.
Hi, Wei. Very nice talk.
Hi.
So yeah, thank you for the talk. So I have two questions, and the first question is in terms of your use the heat flux in the inner core boundary to try to interpret your results. You kind of relate this heat flux heterogeneity to temperature heterogeneity. So as far as I understand, the CMB heat flux heterogeneity, I mean, you can say that's related to temperature, but that may just related to the material, like this, because heat flux is a product of the thermoconductivity and temperature gradient. You could have a temperature gradient difference, of course, but it could be just due to the thermoconductivity of material. It's different.
Yes.
So if you relate that to the inner core boundary, could that be heat flux just because of the like the material is different, like those the so-called cold region and the hot region doesn't exist? It's just the material is different, like, with a different property of thermoconductivity.
Yes, good. That's good question. So in my mind, the answer is I don't know the results. I'm not the expert in this topic, but I think you are right. So yes, you are right. So I'm not sure. The answer is I'm not sure.
Okay. So the other question that I had is I'm not quite familiar with this scattering thing, but as far as I understand, the attenuation, seismic attenuation is very sensitive to green sites.
Yes.
Would you like, because you argue that green sites may be the ultimate reason for this heterogeneity of scattering. Could you also observe the attenuation?
That's a good question. So currently I'm collaborating with one paper. So that paper is do a forward simulation. So for here, so I have not consider. I don't consider the intrinsic attenuation. I only consider about the scattering one. So I think if we want to study the quantitatively how large of the scattering, we should consider about the intrinsic attenuation. So now what we map is the relatively strength of the inner core scattering. So yeah, I think you are right. So the further study and we are doing now is we try to combine the intrinsic and the scattering together to precisely determine the scattering strength. This is what we are doing now.
I see. Yeah. So probably one more question, one related question. You listed four mechanisms that could account for your observations, and you kind of say the first three are not possible. Could you just briefly explain why?
Oh, okay, sure. So for this, we have do some literature study, and also I'm also have a work on the small scale topography at the inner core boundary. So at this strong scatter region, there are different papers to publish about the small scale topography, but at this region, so this is out of the detected region from seismic network. So sometimes we don't know the answer is yes or no. So this is one reason for the topography. And also as I mentioned before, the topography as our only factor cannot be explained the inner core scattering. So for this one, so I just say so we cannot say this is only the region. Okay, this is the only reason. The second one is the partial melt. The partial melt is an interesting one. So one reviewer asked about this one. So the partial melt, there is two. I should be say a little bit carefully. So for the partial melt, so if the liquid become the solid, so there are some porosity. So the porosity maybe contains some liquid inside, and when the inner core become smaller, become larger and larger. So there are two processes. The first is the solidification. The second one is the compaction. So if the compaction dominates, so the partial melt could be go out. The partial melt or the liquid in the porosity could be go out. So the partial melt could be done. But if the inner core grow very fast, the partial melt could be stay in the inner core. So from the geodynamic study, so at the currently the stage, so the partial melt could not be go such deep, but at the early stage of the inner core formed, that could be the partial melt could be a dominant factor. So this is the factor for the partial melt. Okay, so for the compositional variation, this answer is no, because we don't find a lot of we don't find many literature talk about this one. So this depends on different parameters. So we exactly we don't know.
Yeah, but I mean you cannot rule out this possibility, right? Like
yes.
Yeah. Okay. Yeah. Okay. Yeah. Thank you. Thank you very much.
So what I think so what we mentioned in the paper is we find the temperature variation is the dominant and easy to explain the such a large pattern.
Okay. Actually, I have a comment. So on this page, for your 4 bullets you list here. So to me, I think your bullet 1 and 2, to me, you probably, let's say, they are highly correlated. And for bullet 3 and 4, I think they are also highly correlated. You cannot differentiate one against another. Just give you an example. So if you want to use the temperature to explain the heterogeneity, then we know that for the inner core, outer core, they have different compositions. So the light element partitioning, like carbon, sulfur, silicon, their partitioning coefficient, we know they are not 1. So we don't know what exactly, maybe 1.5, maybe 2, or maybe let's say 0.5. So they're not 1. So, but this crystallization process, what the type of composition that crystallized from the outer liquid core, which is highly homogeneous in terms of composition. According to Bruce Buffett, they are homogeneous in ppm scale, so highly homogeneous. Yes. So for that, if you have a different temperature likely to crystallize, that will inevitably introduce a different crystal composition compared with other crystals that crystallize at different temperature. So for me, that your bullet 3 and 4, you cannot differentiate that. So if you have same temperature, then you will have the same composition because they are from same temperature pressure from exact same liquid. But you have different temperature, and then it's inevitable they are going to have a different composition. So it will be a combination of both. But probably here in this room, maybe Du Zhixue has already left, or Deng Jie, probably in the future, they could tell you that what type of temperature leads to what type of composition that are self-consistent with each other. So that's my perspective on it. I think then if we think the temperature is the same, then we will leave that to the non-chemical equilibrium problem. Because to me, that the bullet point 3 and 4 are chemical equilibrium question, which is a very high temperature process. I think that it probably will be homogeneous at a relatively fast scale, including crystal growth, including the crystal grain size, because the temperature is really high. And then on the other hand, then if we are thinking put the chemistry apart, thinking everything is in equilibrium, then you have the other kinetic factors due to disequilibrium chemistry, like the different topography, the compacts of different belt crystal ratio that could lead to the slight difference. So to me, that your bullet point 1 and 2 are highly correlated, and your bullet point 3 and 4 are highly correlated, and it's very hard to convince me that you just use one bullet point to rule out all the others.
Oh, no, yeah. So I just have some addition. Yeah, I agree. Say maybe you're right. And because for this study, we just we find more from the yeah, you are right. We don't focus on the compositional variance because we are not the expert. But there are a lot of experiments and also a lot of the simulation, which use like the HCP and the BCC, different kind of the crystallization structure, and they set up the different temperature. They can generate the different alignment of the crystallization and also different size. And from that size, we can generate a different scattering model. So we just get our conclusion from that study. So I think I agree, you are right. I should just be more careful about the conclusion here. Yes.
Okay, other questions from our participants? Last question. Okay, we have around for a little over an hour, and that's about the right time for us to adjourn our webinar. So we'll take a break for 4 weeks and then come back for another webinar on July 27th, I think. Okay, thank you very much, Wei, for your talk, and thanks everyone for your participation. So have a good day or have a good evening, everyone. Bye-bye.